announcements I want to go through with you are the readings and topics rough schedule is updated. And I did that yesterday morning. We'll take a look at it in a second. I know some of you use it. Special study group signups. Special study group signups, they'll begin at Monday night at 7. And I suggest that you get ready for that. It's going to be a stampede. There'll be a special signups page. It's not accessible to you guys yet, but it will be accessible at 7 p.m. on Monday night. Signing up is going to be first come, first served. And so what that means is at 7 o'clock, there's going to be an enormous buffalo stampede of people to get special study group spots because there's never enough. We never have enough spots for everybody. So, that being the case, just try to get in there fast. There's a special study group schedule page. It is available now. It is visible. And I'm putting together the specs in it. I've got a few people lined up in there and more to come. And so if you're a special study group leader, or if you got a message from me about being a special study group leader, you need to respond to that by tomorrow, or you'll be SOL. You won't be a special study group leader, and you will have to take the final exam. And it's your option. You don't have to be special study group leader if you don't want to be. Okay, attendance and participation is going to be worth 4 points. Justin, are you ready? Okay, let me keep going through this, and we'll get to that. And just a note to you: if you want to participate in special study groups, and you sign up, we'll be expecting you. The special study group leader will know exactly who's going to be in his group. They will take attendance. If you're not there, we will know that you've signed up and not shown up. And that is going to put you on my you-know-what list. Okay? Because there's never enough spots for everybody. So if you take a spot and don't use it and don't show up, you're taking it away from somebody that could really use it. All right? So I'm not going to look kindly on you at all if you don't show up. So look at that schedule page, and for darn tootin', make sure that you are locked and loaded for that session. Otherwise, don't sign up for it. Okay, here's what the rough schedule of topics and readings looks like now. I've updated weeks 9, 10, 11, and 12. 12 is next week. A couple things about it. You can read about the different stuff. We're going to have a demonstration today with Justin. Midterm exam 3, it's actually going to be covering the last few parts of chapter 6 and up to chapter 9. And we're going to be finished the stuff in chapter 9 that we've already done, and the stuff in chapter 9 that we're going to do on Tuesday. And we're going to finish chapter 8 stuff today. We're going to finish lecturing about it. You're going to be working on it over the weekend. All right. Now, the special study group signups page looks like this. There's a red stapler and stuff at the very top. Up near the top is where the link is going to be. You will click on a link. Now, there's no link there now. All right. But 7 p.m. on Monday night, yep. And you'll click on there at 7 o'clock. And if you click there at 7:05, you might be SOL, because it's going to fill really fast. All right, so make sure that you're in there at 6:55 and you're ready to click. All right. Now, also on the page, you'll see a blurb on each of the special study group leader, where they're going to meet, and their photo, so you recognize them. And here's Chelsea. She doesn't have her specs yet, but she will. And the rest, there's a few people lower down the page. She's just number 1. And so definitely scope out the few, like 2 or 3 different sessions that fit your schedule. And side note to SSG leaders, you don't sign students up. They sign up to your group. Okay, so you just, you're going to be in your group. I'll set that up. And then there'll be 6 other students to sign up, and it just is whoever can get in there. Okay, so you don't get a chance to choose. They choose you. All right? So that's how it works. So find some that fit your schedule, and that'll be good. And hopefully you get your first choice. But if not, if you've got a couple 3 that you've selected, maybe you'll get one of your backups. All right, let me pause the. Okay. Now, last time we talked about this representation of an oscillating system in phase space. Phase space being the 2-dimensional abstract space in which one of the dimensions is momentum and the other dimension is a position coordinate. Fellas, you're distracting me. Don't talk over the top of me, please. All right, we've got a lot of stuff to cover. Okay, so we talked about, and one of the landmarks, for instance, is up here at the very top of the ellipse. Maximum momentum, P max. And over here on the far right, X max. X max, comma 0, the maximum positive value here of the X coordinate. The shape of this is controlled basically by F equals ma and the energy and everything. But this is a different way to represent it, and it encodes a lot of physics and actually a lot of calculus. But this is for an oscillating system. If we were to look at phase space for a free fall system, like this guy jumping out of a perfectly good weather balloon, can you imagine this guy at this instant? Man, I'd be totally having a heart attack, man. That took some nerve. But he looks pretty cool, just jumping right out there. Anyways, here's what a free fall phase space diagram would look like. And I'm going to ask you some questions about this diagram. So I'll get your clicker ready. And this curve, the vertical axis is the momentum axis. Now look at it carefully. Look at the labeling. It says the y component. So this is a vertical. This is free fall. So the y-axis is here. The sideways or horizontal axis is the y component. Now normally, if we're trying to use graph paper to represent like a map, like a map of the USA, X and Y are sideways and up, and Y is, like this. But in this one, this is an abstract. So this is not a picture. This is not a map that you can take a picture of, like you could take a picture of the United States from space and then transfer it into a regular XY plot on paper. This one you can't. You can't photograph this, but it still encodes a lot of information for us. Now, I'm going to ask you a clicker question now. Let me get it started here. Here's your first clicker question. And I want you to think very carefully about this. Describe the motion based on visual inspection of the phase diagram or the phase portrait. For a free fall object, and this one's at 1 kilogram. I just made the numbers fairly easy. Read that carefully. And I'm going to give you, in just a second, I'm going to show you the main diagram again. All right, but read through these options, A, B, C, and D. And I want you to choose whichever one you think is good. right, now if you want to adjust your diagram, here's a big version of the diagram. I'll go back to the options in just a second. Go ahead and re-verify your notes. All right. And the y dimension horizontally goes from negative 100 meters to positive 100 meters. And then the momentum dimension vertically from negative 50 kilogram meters per second to positive 50 kilogram meters per second. So the question is, which of these 5 descriptions is kosher? Good, and you can talk and visit with your neighbor if you like. Talk it over. I see a bunch of people kind of thinking it over. This is not an easy question, but so I want you to think carefully. And sorry, you guys over here, the projectors, I don't know what's going on with that one. I'll give you another minute. "15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys voted for. All right, let's look at these options. Option A. 9% of you voted for option A. Starts at maximum y, then moves left, slowing down. What? There's no left or right in this. It's vertical. This is the motion along the y-axis. All right, so this one right away, it's out of here. All right, so if you voted for that, mark down why it's wrong. Let's look at B. It's falling straight down, acquiring more and more downward momentum. Downward momentum is what? The left or right side, or the top or bottom side? Downward momentum. Left? Incorrect. Incorrect. Yeah. The top is upward momentum. It's positive. So when you have positive y momentum, that means you're going this way. Negative means, so yeah, this one, all the states are mapped out at 1 second apart. And it's on the bottom half. So this is actually ding. And a bunch of you, 34% chose that. C. Let's look at the other ones, just in case. 7% of you voted for C. It's like a baseball pop-up, heading up, straight up, and then straight down. Where's the heading up? There's no heading up in this. Heading upward means you have some positive y momentum. And Sarah, we haven't got any of that. Okay, so C is out. D moves left to right at faster. Okay, left and right is out of here. Right. Now, option E. It's launched upward from about level y equals negative 20 meters, then it slows down and stops, like being caught by a baseball player at y equals 100 meters. That actually is also correct. Now, the difference in these two is important, and I want you to make a note of this. The phase diagram can be interpreted for the direction of time. If I say that the initial position is y equals negative 20 meters, then that means my phase or my dynamical state evolves from lower left to upper right. If I say that my initial state is y equals 100, momentum is equal to 0, then that means my state evolves down here to the lower left. There's a direction of time. That is also true in the ellipse. If you analyze the motion of an ellipse, a physical oscillator, I should say, it will correspond to one or the other direction clockwise or counterclockwise on the phase space diagram. Another interesting thing about the phase space ellipse is for an oscillator, it encloses a certain amount of surface area. The area of an ellipse is particularly simple. Its circumference is tough, but ellipse is, the area is pretty basic. It's pi times half the width times half the height. Now, in math class, here's half the width, and that's the long axis, so we would call that the semi-major axis. And then half the height, that's this guy up here from the origin up to the top of the ellipse, and that's the shorter dimension of the ellipse, so that would be called the semi-minor axis. Let me move it off to the side here so you can see it. Those are the two dimensions. So the area is pi times half the width of your ellipse times half the height. And if you think about it, a circle is an ellipse for which the width and the height are exactly the same. Therefore, A and B are the same, and we customarily replace the symbols A and B with the symbol R for the radius. And then the area is good old pi r squared. So this formula actually holds for the special case of a circle in which A and B are the same. So this is all lovely. Now, dynamically speaking, here's the area. Pi times half the width, x max in this diagram, times half the height, semi-minor axis, p max in this diagram. And notice that dimensions of the area are right. It's angular momentum or action, a meter times a kilogram meter per second, so that's kilogram meter squared per second. That's angular momentum or action. But what is the dynamical interpretation of the area? I mean, the area is nice. It's important. It's, pi times AB. It's, everything's cool. What is the dynamical interpretation of that? Well, my wonderful students, just as the trip around the ellipse, clockwise or anti-clockwise, gives you an interpretation of time, the area is also related to the meaning of time itself. And so it's a profound thing. And we'll be talking more about it as we go through the semester. For right now, it's a sneak preview of another mountain that we're going to take a look at when we get to the top of the mountain we're on right now, the periodic table. All right, so let's get back to the forces on nearby charged neighbors. The problems that we were working at the end of class, we had, let's see, we had a pair of protons, I think, and an electron, and I asked you what the direction of the net force was at the end of lecture. We want to figure out molecules, and we're going to be working on this nearest neighbor model and multiple neighbors for protons and electrons because we want to apply some of the understanding of that to molecules which are kind of tough. Okay, so we're going to be doing a problem today, a linear array of charges, and it's going to help us prepare to understand molecules. For instance, water has what we call a polarized structure, and that means, sorry, this is not very red over here. The far end of the H atom here, the hydrogen atom, is supposed to be red. On YouTube, it will be red. It'll look nice. The projector here doesn't do reds very well, I guess. The side of this upper hydrogen atom, the side that's towards the right side of it, toward the oxygen atom, is supposed to be bluish. Now the reason for that is that the electron, the blue part of the hydrogen atom, tends to be between the hydrogen atom and the oxygen. That's how they bond. Okay, so the negative end is going to be the oxygen, and that's up here in the direction of this arrow. It's a symmetric molecule. It's a fairly simple one. The angle that the two hydrogens make, center to center of the H to center of the oxygen to center of the other H, it's about 104.4776 degrees. We can measure it pretty good. And there's ways to make it oscillate and wobble and stuff, but the nominal value of that, so it's a little bit bigger than 90. So make that angle, if you can, and obtuse. It's a pretty wide V. All right, and this one's kind of tilted a little bit to the left. Similarly, the distances from hydrogen to oxygen are the same, and they're about 0.0958 nanometers. Now, last time I mentioned that nanometers is the convenient scale for atoms, and so the distance here is a small portion, not a tiny portion, but 0.0958 is not too bad. It's a fairly good fraction of a nanometer. In scientific notation, that would be 9.58 times 10 to the minus 11 meters. So meters are not so good for measuring atoms, but nanometers are good. Okay, and that's the size of this one. And all of this is basically controlled by the F equals ma of the two hydrogens and the electrons and the oxygen and the oxygen's electrons, and how the Coulomb interaction controls the F equals ma and the arrangement of the water molecule. Now think about other molecules that you have heard of. For instance, DNA, extremely large and actually, I won't say that DNA is extremely complex, but it's really big. Any DNA molecule, for no matter what the species is, the DNA is going to be a big molecule, big chain, the famous double helix shape. So we want to try to get down the bottom of these charges. Why do they take this shape? Okay. So today what we're going to do is try to work on some simple charge arrays that will help us tackle something tricky like water, or even something fantastically tricky like DNA. All right, so let's go back to the Coulomb interaction question.
How come it's more negative on the side that the oxygen?
Between the hydrogen's electron tends to be attracted to the oxygen. And that drives the oxygen's electrons to the far side of the oxygen. Okay, so because negatives repel and stuff. So the way it works out, it kind of polarizes the entire molecule. Now, not all molecules are polarized like that, but yeah, this one is. So here's the force law, F equals KQ1, Q2 over R squared. And remember, in my visual coding, red stands for positive, blue stands for negative. And you can have different size charges. Now, what we're going to be working with today is only electrons and protons. So they have the same size charge, but it doesn't have to be. Everything that we do with electrons and protons, you can do with nuclei, which are multiple positive charge net inside a nucleus. Okay, and here's my, the factors are the two charges. How much charge do they have? And then the distance r between the two charges. Now, you have your calculator ready. I'm going to ask you some questions. And make sure you have this force law written down because we're going to be looking at some of the implications of this force law. Okay? And I'm going to ask you in terms of this pair, same pair, Q1 and Q2, basic IQ test. Which pair of force arrows is correct? If Q1 is positive, it's red. And if Q2 is negative, it's blue. Right? Which pair of arrows? Or neither? Is it A, is it B, or is it neither? Option C. "15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. And it looks like 83% of you chose pair 2. That is correct. And the reason is, if you didn't choose pair 2, here's the reason. Opposites attract. So number 1 is going to get some newtons towards number 2. And number 2 is going to get some newtons toward number 1. Question, Isaiah. If we're just asking about direction, only the relative charges matters. So if it might be 1 Coulomb or 1 nanocoulomb, plus 2 coulombs or negative 3 nanocoulombs, whatever they are, the SIGN tells you whether they attract, or the pair of charges, the pair of signs. Plus minus, minus plus, attract, plus plus, repel, minus minus, repel. Okay, that's what we're asking for. All right, another question. Separation D is equal between the protons, the middle proton and the right proton, and between the electron and the middle proton. How large is the electron? And students, I'm asking you, how large is the interaction between the electron and the right? So if you're taking notes, the rightmost proton. All right. I see some wise guy voted for E. The cake is alive. Why are you voting for it? You just never learned. I don't know. 10, 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Well, 70%, no, 39% of you voted for 40. 35% of you voted for B. So that's smaller than the people. You know, A is incorrect. And it's incredible. Fewer people voted for option B, 35%. And actually, both of those are wrong. The right answer is 10. And 25% of you voted for that. Now, I want to go, since so many of you missed that one, I have an explanation. Oh, side note, the word micro always means a millionth. And it's abbreviated with the Greek letter mu, lowercase mu. And scientific notation, 10 to the minus 6. So a micronewton is 10 to the minus 6 newtons. So that's just a notation note. Now, let's get down to business. Why is it 10 micronewtons? And notice that that's 1/4 of the nearest neighbor force. You know, here's your array. These two protons, 40 micronewtons, the interaction force. But the electron over here and this rightmost proton, different size altogether. So let's go and look through that. So first force to write down is the given information. The force between the two protons. Now I haven't put a minus sign in there. I haven't, and you could if you want to talk about directionality, but we're just talking about sizes here. Okay, Isaiah, so you know you've got separate decisions. You've got directionality to figure out, and then you've got sizes to figure out. So it's a set of things that you've got to sort through in your mind. Now, according to Coulomb's law, the force between two protons is Coulomb's constant K times the charge of the first proton, E, and Morgan times the charge of the second proton, another E up there. And then down below, the square of the distance between them. So that's D squared. And if you put it compactly, it looks like this. E squared K times E squared over D squared. All right, so make a note of that. That's my nearest neighbor force. Now, the next neighbor out is the electron. So the electron and the rightmost proton, they have an interaction force too. Now look at the numerator. It's K times minus E, that's the charge of the electron, negative E. And then regular E, that's the charge of the proton. Okay? And then in the denominator now, I have a bigger distance, and I square it. So it's 2D quantity squared. All right? And so I park my minus sign out here. And look, my numerator is the same as the other one, KE squared. And hey, you guys, all the problems that we're going to be working on, you're going to be working with protons and or electrons. All right, so you're always going to have a KE. You don't have to actually make this calculation. All you have to remember is proportionality. But this is why the proportionality works. Okay, now the denominator, look at that. 2D quantity squared is 4D squared. All right? Now you may be thinking, oh, Dr. B, nice, very good, 4D squared in the denominator. You know, how does that affect the Chick-fil-A strips that I want to have for my lunch? Well, park that negative 1/4 out in front, And look at what you got left. K e squared over d squared. You got a minus 1/4 and then a k e squared over d squared. Ding! That's the proton-proton. That's the nearest neighbor force. And this is why if you double the distance, the interaction force goes down by 1/4, or the shrink down factor is 1/4. All right? Now, questions before I keep going? Yes? This one? That represents the force of the electron on the proton to the rightmost proton. Okay? This one, the force of the middle proton on the rightmost proton. Okay? Yes?
So how would you plug in what numbers to find any type of answer? I'm not sure.
What we're going to be doing is focusing on this distance factor.
Okay.
All right? So let me go to the next slide and we'll work it out. The Coulomb interaction is based on the square of the distance. And Ashley,
Yes, sir.
right.
That's
It's a pairwise interaction, so you go pair by pair. So if you have one particle that you're trying to figure out F equals ma for, you go to all of its neighbors, your target particle and the first neighbor, target particle and the next neighbor. So it's always going to play out with the r squared. So an example of that is if they're double the distance, then the shrink down factor is 1/4. Right? So the second neighbor out compared to the nearest neighbor force, NF, that's my normal acronym for that, is 1/4. If you go 3 times, so here's the target. All right, so here's my target particle. And here's my nearest neighbor, another proton. And I've got another one out here we'll talk about. This is the generic case. But if you're second neighbor out, which we just did, if you're 3 times the distance, if it's triple the distance to the third neighbor, all right, then your shrink down factor is 1/9. Because you're going to have a 3D quantity squared in the denominator. And that works out to a 9D squared in the denominator. And then that's going to give you a shrink down factor of 1/9. And then you also have to decide, is it going to be leftward or rightward? Is it going to be an attraction or repulsion? That's separate. But for the size of each of these forces, yeah, in general, for the nth neighbor, which I kind of put a squiggle here to mean here in the middle of this horizontal line segment to indicate kind of some unknown distance. Okay, so we're skipping out to the nth neighbor, and we're not thinking about the other neighbors. We're just thinking about the nth neighbor and my target. The shrink down factor is 1/n, or a 1/nth of the nearest neighbor force. So whatever the nearest neighbor force is, if you know that, and you know the distance ratios, you can get it. All right, question? Okay, let's keep going. So now remember, now here's another array. We're going to work on some more arrays here. I'm just going to go through it step by step. And we're aiming for molecules. Now this is a kind of a schematic or idealized molecule. And we're going to try to hack it. All right, and see what we can see. And here's our strategy. If you know the nearest neighbor force, like 40 micronewtons. And if you know the distance ratios, if you know that you've got all the same distances in between each neighbor, then you can get the net force on any one of the particles in your array. Right? So that's your strategy. You've got, and on your homework over the weekend, I'll always give you a number for the nearest neighbor force. And I'll always give you an array of equally spaced protons and electrons. Protons and or electrons. And let's work on this one. So go ahead and sketch. An electron, this is our target particle. The nearest neighbor is a proton. And so our leftmost electron is the target particle. And the second neighbor out from my target is another electron. And then my third neighbor out is a proton. And then my fourth neighbor out is another proton. And they're equally spaced. Okay, now, let's say that the nearest neighbor interaction right in here between these two babies, my target particle, the electron on the left, and its nearest neighbor, a proton. Let's say that that nearest neighbor force is 288 nanonewtons. All right? Now, all the other neighbor forces are going to be fractions of that. If I know it's 288, then everything else is going to be a fraction of 288. All right? And that's, so think about it as your toehold to figure out all the other distant neighbor interaction forces. Right? And we're going to go item by item through this thing. So let's do the second neighbor. Okay, we know the nearest neighbor, that's 288. Okay, second neighbor. Twice as far as the nearest neighbor distance. So the electron to electron repulsion, see Isaiah, you got to figure out what if you got enough repulsion or not. And then you got to figure out the size. And in this case, it's a fourth of whatever the nearest neighbor had. Yes?
So it just gets a fourth smaller every time you go out?
No, not every time. Only for the second neighbor. Now the third neighbor is going to have a different one. But let's get this one done. All right, so let's go ahead and draw a dot somewhere. And let's attach a big, nice arrow. That one, that's a rightward arrow representing a rightward pull on the electron from its nearest neighbor proton. Its nearest neighbor proton is over there to the right, so that electron is going to get pulled to the right with 288 nanonewtons. Now, we just figured out the repulsion force. It's 72, and because it's repulsion, that leftmost electron, it gets repelled over here to the left. So we give that a minus 72 nanonewtons. All right? So now we've got the second neighbor. We got a bunch of other neighbors, so let's just keep going. All right? And we'll come back to this diagram. You're still working with this. Let's get the pull force from the second proton. So that's this one here. That's neighbor number 3. All right? We want to figure out, okay, it's going to be pulling the electron on the left. It's going to be pulling that electron over there. If it can, it's going to. So pair by pair, the target particle with the third neighbor. All right? So here's the line segment representing the distance, center to center, from my target on the left all the way to my third neighbor. And hey, you guys, that's 3 times the nearest neighbor distance. So now, instead of a fourth, Ashley, we get a ninth. All right? A ninth of 288.
So it's not like each number that you've got that new neighbor, and then you do the 1/9. It's just that the target.
You go with the nearest neighbor every time. The nearest neighbor tells you, in this kind of a problem, what all the other interaction forces will be, if you know the distances. Which,
So is it negative 32 then?
no, it's positive 32, because it's pulling it to the right. All right, so it's a 32 Newton or 32 nanonewton force, and it's a proton pulling off to the right on the leftmost electron. So I'm going to pencil in a little teeny arrow to the right, 32 nanonewtons. And hey, you guys, by the way, these arrows are the right sizes. They're proportional. Okay, I was very careful about doing that. All right. So now I've got the third neighbor attraction force. Ching! I got one more to go. Now, we could add all these babies up if we want, but we got one more neighbor. All right, that's the last one. Neighbor number 4, down the street. Sarah.
All of these numbers are relative to the first electron?
Yep, that's what I'm telling you. And the reason for that, Sarah, remember how before we got ke squared over d squared? It's always going to be like that if you only use protons and electrons. So this is like a workout to help you with oxygens and hydrogens. Now we're doing only protons, only electrons, so it's always going to be ke squared on top. And then if they're spaced out equally, you're always going to get these d's, 2d's, 3d's, quantity squared in the denominator. Right? And then you got to decide the directions as well. All right. Let's get the weakest pull force from the third proton, neighbor number 4. Okay, here's the line segment to represent its distance. And it is 4 times the baseline nearest neighbor distance. All right, so my shrink down factor here is 1 over 16. 288 divided by 16 is 18. And hey, you guys, you know, I secretly knew that 218 would be divided by 16, 9, and 2 nicely, so that's why I did that. Or 16, 9, and 4. Anyways, so 18 nanonewtons to the right. So this is the tiniest of all the 3. Excuse me, all the 4. And let me just introduce a vocabulary term for you. These are the 4 constituent forces from which you calculate the net force. Okay, the net force is comprised of these 4, in this case, constituent forces. If I give you a different array, you might have 2 constituent forces. A bigger array, you might have 5 or 6 constituent forces. But the same strategy applies, each pair by pair, neighbor by neighbor. Okay? So now what you can do is just add them up. And this is where knowing the direction is important. If you don't have the direction right, you're not going to get the right net force. You know, so if you haven't figured out that electron repels the target particle on the left, the leftmost electron, you're not going to have a minus sign there, and you need one. Isaiah. It's tricky. You got first you got to look at your pair and say, all right, do they attract or repel? All right. Now, if your target's over here, you got to think about a repel is going to be this way. And attraction is going to be over here. But if I tell you, well, let's work on the rightmost proton, and then here's your other neighbor, all right? A repel is going to be left, and attract is going to be right. So figure out if it's a repel or attract, then figure out its direction, then figure out its size. And then when you're done with all the pairs, add them all up. Right? So when you add them all up, you get 266 nanonewtons. And there you have it. Now we're going to work through a few more clicker questions together. And we're going to just do a few of the basic decisions like what I was just talking about with Isaiah and with Ashley up here in the front. And we're going to go through these things. And so have your clicker ready. And here's your sketch. This is a bigger array. This one's got, no, this is the same size, but it's different. Now my target particle is the leftmost electron, but I have a slightly different set of neighbors. Proton is the nearest neighbor, but then I have electron, electron, and finally a proton. So this is a different set, but we can still do it, do everything the same way we did before. Everything's kosher. The nearest neighbor force is 576. Let's try that one. Okay, Brian? Basic. All right. And we're going to calculate this electron on the left, and we're not going to finish the calculation in class. But what we are going to do, I don't know, maybe we'll finish it. Either we'll finish it or we'll do something else. So 576 for nearest neighbor. Now, let me ask you this question. The force of the leftmost proton on the leftmost electron, okay, leftmost electron, that's my target. So put a question mark next to your leftmost electron, above it or to the right of it or something like that. Just to mark target. That's my target. See how this goes, Isaiah? Is it a rightward attraction or is it a leftward attraction? Is it a rightward repulsion or is it a leftward repulsion? It's, depending on what you got. One of those is correct, and only one, for this array. But some other option might be correct for a different array. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys got here. Uh-huh. Wow, you guys are geniuses. The morning class got blazed up on this when they got tripped up. Yeah, attraction rightward. The proton is going to try to pull the electron to the right. All right? So you got to know if it's an attraction, and you got to know then, all right, is it a rightward or leftward? And it's rightward in this case. Next question. Force on the center electron. From the center electron on the leftmost electron. Same decision. See, because when you're tackling this calculation, you've got a bunch of decisions to make. And you got to do them in order. And if you mistake one of the decisions, your calculation is going to be off. Oh, my wonderful students. This is the genius section, I guess. Did you ever think about that? Did you know that you're in the genius section? Specially selected? Who knew? But there it is. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you jokers have got going here. Pretty good. 67%. Yeah, repulsion. So electron to electron is repulsion. Okay. And so this baby here in the middle, this is the neighbor. It repels my target particle the other direction, to the left. Now you know that you've got to put a minus, and figure out the size now, and give it a minus sign. And then, go to the next pair. All right? So, let's so far, let's look at what we got. We got a little bit of rightward and we got a little bit of leftward. All right, but we still have to figure out the sizes. And then, so we don't have the exact arrows, but we got a leftward arrow and we got a rightward one. And then we got to do size and direction for these two babies over here. We haven't even tackled them yet. We haven't tackled the first thing about it. So let's do that now. Let's try the leftmost electron and all the way over the rightmost proton. So here's your pair. This baby over here, the rightmost proton, and what effect in terms of nanonewtons does it have on my target electron over here on the left? And let me get this question started. The NNF is 576 nanonewtons. All right. So now we want to figure out the size. And you may have noticed that 288 times 2 is equal to 576. Okay, 20 seconds. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. You know, this is interesting. 169 people voted on this one. 167 voted on the previous question. The question previous to that, 168. So when you guys see the fact that you don't get all the points in clicking, that's why you don't answer in time. A few of you. So, gosh, you guys are blazing. So that means you're ready to put it all together in homework 14. So let's dismiss. Be ready for special study groups Monday night, and I'll see you next Tuesday. Special study group leaders, can you come up here for just a moment? Special study group leaders, can you come? Special study group leaders. She ain't listening.